Hello everyone, Sean McCartney and I both welcome you back to this session on monitoring water quality of inland lakes using remote sensing, part 3. We're going to focus on assessing water quality using satellite and in situ observations today. We already had our first two sessions and today is the concluding session of this webinar series. Just a note here that homework will be posted today on our website. It is also available from the meeting site and will be due on 8th of August. We started with overall training objectives as listed here, so that by the end of this training, you should be able to identify remote sensing observations useful for assessing water quality parameters in inland lakes, recognize the importance of in situ measurements together with satellite observations in developing methodologies for operational water quality monitoring, obtain an overview of Cyanobacteria Assessment Network or CYAN, an early warning system to assess algal blooms in freshwater lakes, and access satellite data and develop methodologies to assess water quality parameters, more like see how to develop methodologies, and we'll talk about it later today. In part 1, we saw state-of-the-art high spatial and spectral resolution observations from Landsat 8, Sentinel-2, and Sentinel-3 for water quality remote sensing. We described selected open-source in situ measurements of water quality parameters, including from USGS Water Dashboard and Lake Water Quality Portal, National Harmonized Chlorophyll Data, UNEP GEMSTAT, and Gloria. We reviewed algorithm development requirements for remote sensing of water quality parameters, explored and downloaded Gloria in situ measurements of chlorophyll A concentration, total suspended solids, and Secchi depth for Lake Erie, and searched and identified optical surface reflectance data from Landsat 8 and Sentinel-2, co-located with in situ measurements for lake area using Google Earth Engine. Last session was about CYAN. We learned description of Cyanobacteria Assessment Network. So CI or Cyanobacteria Index data products are available daily and at 7-day maximum value composites from MERIS ENVISAT satellite, which is 2002 to 2012, and the current period starting from 2016 to present, it's covered by Sentinel-3A OLCI and Sentinel-3B OLCI. We had a demonstration and application of CYAN Web App, and you also had some hands-on exercise with CYAN Web App. That brings us to our today's session, assess water quality using satellite and in situ observations. Sean and I will be doing this webinar today. And for today, the objectives are listed here. By the end of this session, you'll be able to identify NASA image processing software for water quality monitoring, understand strengths and limitations of remote sensing and available in situ data for inland water quality monitoring, describe upcoming NASA missions relevant for water quality monitoring, and derive statistical algorithm coefficients for getting chlorophyll A concentration and total suspended solids. Also, we will touch on how to get water clarity using satellite spectral reflectance and in situ water quality measurements. We'll do this using GEE. And so the outline is, we'll start with a brief introduction to NASA image processing software for water quality monitoring. We'll go over strengths and limitations of observations of water quality monitoring, both in situ and satellite, and we'll have overview of upcoming NASA missions. Then Sean McCartney will have a demonstration and exercise and derive statistical algorithm coefficients for getting water quality parameters. We'll focus on these two, considering the time availability, chlorophyll A, and total suspended solids in GEE. And you will also get some idea of how to get Secchi depth or water clarity using similar method. And then we'll summarize what we did in this series. So next we have a brief overview of NASA image processing software for water quality monitoring. In this training, we have been using Google Earth Engine to get Sentinel-2 and Landsat-8 images, which are already level 2, which means that they're processed and we have atmospherically corrected surface reflectances. Now, NASA software CDAS that allows more flexible calculations. You start with top of atmosphere reflectance and you can choose atmospheric correction process and come up with level 2 water living reflectances. It's a very widely used software, pretty sophisticated. So CDAS, it's NASA Ocean Biology official data processing and analysis software. The latest version is 8.3.10. In earlier ARSET webinars have introduced CDAS and used as well, earlier versions of course. And there is a graphical user interface or GUI version for CDAS, as well as can also be downloaded, and the code can be used as command line version if you want to do bulk processing. It's open source and can be downloaded from this link here. CDAS webpage has a lot of information about this software and tutorial also. It's available for Windows, Mac OS, and Linux operating systems. Earlier, it was not available for Windows, but it is now. And it requires Bash, Python 3.6 or later, Python requests package version 2.8 or later, and installer and source code, they're available from CDAS website, and the links are available through this slide here. So the CDAS GUI can be used for visualization, processing, and analysis of images. It's easier. You don't have to code anything. You just click and get the data through GUI. Installation of OCSSW is required for converting data from different levels, level 1 to 2 or 2 to 3. And running OCSSW can get you level 2 and level 3 data from level 1. Accessing available in situ data from CBAS. We talked about CBAS in part 1, which are in situ data mostly in estuary and open ocean, but there are some inland lake data available as well. So they are available through CDAS. You can automatically load those observations in there. CDAS 8.3.10 that contains CDAS toolbox that includes Sentinel-3 toolbox. Earlier, Sentinel-3 OG was not included in here. CDAS OCSSW can allow atmospheric correction options. It requires downloading level 1 satellite images for processing. And you can look at this earlier webinar for a demonstration of CDAS and its features. But in this training, we focused on GEE because you're not downloading any data. You can just work on the cloud environment and process the data and visualize. So that is just for your information that you can explore that if you want more options and you want to start with top of atmosphere radiances or reflectances and want to correct data for atmospheric correction and come up with your own surface reflectances, you can do that. So let's look at strengths and limitations of observations of water quality monitoring. So advantages of remote sensing for freshwater systems. Satellite has long-term imagery available. It's a long record, so it's not intermittent, it's continuous, such as Landsat, it's available since 1972. MODIS also since 1999. VIIRS then, and then Sentinel-2 and 3 MSIOLG. So ongoing commitment for space agencies to continue data collection. So more and more missions and improved missions with better observing capability are planned. Reliable data for operational early warning and forecasting systems. Landsat and Sentinel-2 have sensors with moderate to high spatial resolution appropriate for lakes. And all these data are open source. So these are some major advantages of remote sensing data for freshwater system water quality monitoring. There are also limitations of using remote sensing for water quality monitoring in lakes. First of all, if the water body is shallow, then interference from the bottom, so bottom reflectance, it has to be corrected for, or it adds inaccuracy in your water quality parameter retrieval. So water bodies too small cannot be resolved from some sensors. We talked about it that roughly at least 3 pixels are needed within the water body away from the shoreline. And so which water bodies or lakes would be resolved by which sensor, that is dependent on sensor resolution. There are limited number of standard algorithms for these optically complex waters. What that means is that each lake or reservoir or water body, you have to develop your own algorithm, and for that you need in situ data. So there's no one algorithm that fits all the water bodies. Atmospheric correction is a challenge because you need information about gaseous molecules in the atmosphere, but also about clouds and aerosols. Also, optical sensors, they cannot see through clouds, and so whenever there is cloudy condition, you cannot see the surface and you cannot get water quality information. Ground truthing is costly. There are not very frequent ground measurements for either algorithm development or for validation, but they are absolutely required. So co-locations of satellite observations and surface measurements, both in space and time, are required for algorithm development and for accurate retrievals of water quality parameters. And that also doesn't happen, as we saw in section 1 when we're trying to match Gloria data with satellite data. We don't have that many matches. We do have in situ data, but we don't have satellite overpass on the same day. Or when we have satellite overpass, we don't have in situ data. So there is recommendation for in situ data collection. NASA Ocean Color provides overpass time for various satellites for selected geographic region. And here is the web page or link you can go to, and it's an overpass predictor. You can go here and look at different satellites and pick latitude and longitude and geographical region and time, and it tells you when there will be satellite overpass over the lake of your interest. And then you can plan to go out and take water samples during that time, so you have co-located data. So collecting in situ water samples within 2 to 4 hours window of the satellite overpass would greatly benefit algorithm development and activities. That way you know that when satellite is looking, that's when you have in situ data. Relationship can be derived between that, and that can be used. So that brings us to upcoming NASA missions, and there are 3 of them. The first one is Plankton Aerosol Cloud Ocean Ecosystem, or PACE. This is planned for launch in early 2024, actually January 2024. It has advanced optical spectrometer, ocean color instrument, or OCI, which is hyperspectral measurements of water quality products. So ultraviolet to near infrared range is covered by this instrument. SBG is Surface Biology and Geology. That will be launched in 2027-28 timeframe. It's in the initial phase of development. That will also have hyperspectral imagery from visible and shortwave infrared range, and it will be multi or hyperspectral imagery in the thermal IR. It will also have thermal IR. Glimmer is going to be one mission that will be in geostationary orbit. And so that is also planned to launch in 26-27 timeframe. It will have hyperspectral imager and a landmark imager, and will provide information on harmful algal bloom, oil spills, and sargassum accumulation. So geostationary orbit, that means It will provide more frequent observations, or diurnal observation can be obtained over waters, and it will help in resolving diurnal cycle of many water quality parameters. It will be placed somewhere between 88 to 108 degrees, so it will look at this part of the world and focus on 1/3 of the Earth disk. As you know, geostationary orbit looks at partial Earth disk, and it will focus on this region and provide this information. So we want to talk about PACE in a little more detail because its upcoming mission. These slides are provided to us by Natasha Sadov. She is the PACE Applications Deputy Coordinator. And so thank you, Natasha. So here is the information about the mission. PACE is NASA's next great investment in hyperspectral Earth imagery and multi-angle polarimetry. And as mentioned, it will be launched in January 2024. It's designed to have 3-year lifespan and 10-year propellant. Hyperspectral imager, OCI, spectral resolution will be high, so UV to shortwave IR 340 to 890 nanometer. Every 2.5 nanometer there will be observation, and then there will be other wavelengths as well. Temporal resolution will be 2 days. Spatial resolution would be 1 kilometer square at nadir. There will be 2 multi-angle polarimeters, HARP2, which would be wide swath with vision NIR, near IR, and then SPEX1, narrow swath, and that's hyperspectral UV NIR with multiple viewing angles. So the instruments will help resolve different algal groups, dark ocean versus bright land and clouds, image stripes, sun glint, absorbing aerosols. All these information will be obtained from PACE instruments. So if you go through this detail, you will learn more about what will be the measurements and how it will expand our current knowledge. So the main idea is to moving from multispectral radiometry to spectroscopy, and these are the historical missions starting from 1978 all the way to VIIRS here, and this is the range. You can see that all these instruments start from blue and go to shortwave IR. PACE will start with UV and go to shortwave IR with hyperspectral resolution, and it will help in dissolved organic matter can be derived from this, absorbing aerosols. Phytoplankton community composition can be derived, as well as phytoplankton physiology. So these are some of the additional benefits. And one example you can see from VIIRS, these dots, they show fish food and turtle food. So these are diatoms. And this is what PACE OCI will see because of hyperspectral nature of the instrument. So PACE data products are listed here. There are standard products will be chlorophyll A, diffuse attenuation coefficient between 400 and 700, absorption coefficient of colored dissolved organic matter plus depigmented particles of 440 nanometer, particle backscatter coefficient, phytoplankton carbon apparent visible wavelength, and there will also be provisional or experimental products, suspended particulate matter, absorption coefficient of colored dissolved organic matter, phycocyanin or cyanobacteria, floating algae flag will be there. The other pigments will be dissolved. Phytoplankton community composition will be available. And there will be water quality product suite. This is tentative, but then these are all the products that you can look forward to once the PACE is in space. More information can be found about PACE. If you want to join, there is a workshop coming up in early September. You can register for it. It will be focusing on PACE applications. So with that, we want to focus now on statistical algorithm development for acquiring water quality parameters. You recall this diagram, we got in situ data for Lake Erie here from Gloria. We obtained Landsat 8, Sentinel-2 data for using GEE. So today now, the focus will be on model coefficient development that we can then apply to other images to derive water quality parameter. So we'll start with this algorithm development procedure. Just to note about atmospheric correction, we've already talked about its importance and that it requires radiative transfer modeling along with atmospheric conditions, clouds, and aerosol information. So there are various techniques. NASA Ocean Biology Processing Group has an algorithm. You can learn more about it. There is USGS, second simulation of the satellite signal in the solar spectrum. This is 6S that has been used. So Landsat data that we use is corrected using 6S. And then there is Ecolite. This is European software that provides atmospheric correction, and Hydrolite. That also is available. I think NOAA uses this atmospheric correction. So this is just for your information that atmospheric correction has to be done. CDAS has that option inbuilt that you can use to correct data, atmospherically correct data. So what we are going to use when Sean McCartney is going to show how to the methodology to develop algorithm to derive water quality parameter using GEE. So there are various models for deriving water quality parameters. Most of them are statistical and empirical. As we talked about earlier, each water body needs its own algorithm, and they can be quite simple to quite complex. For demonstration purposes, here is what we are following. So for chlorophyll A, we are going to use its color index or CI, and that is defined from surface reflectance in green, and this is blue, and so green minus, this is the wavelength difference in green and blue and red and blue, and this is the reflectance difference between red and blue. So this algorithm was derived starting from sea waves to MODIS, and it's been used to get chlorophyll A concentration. Here is the reference, Hu et al. Describes CI, and so what you do is you have in situ observations of chlorophyll. You take log 10 of that value and find co-located satellite images to calculate CI, and then fit a regression line to find coefficients A0 and A1, which are line fit, intercept, and slope, and then use those to calculate chlorophyll A concentration based on CI for locations where you don't have in situ data, or for images for which you don't have in situ data. This works mostly for low range of chlorophyll A concentration. So the current version of algorithm that NASA uses is OC4, it is called. It's a fourth order polynomial fit. It's applied to blue-green reflectance ratio. And so there are 5 coefficients that you need to get a log 10 of chlorophyll A concentration. In GEE, it's difficult to do this part. You have to do it offline and then use coefficient to calculate chlorophyll A. So for demonstration, we are going to focus on CI, but you can use other software like Python or IDL or R or MATLAB to fit fourth order polynomial if chlorophyll values are high, and then you get more accurate chlorophyll concentration from that. There are models for TSS and Secchi depth, which represent water clarity. So, if you search the literature, there are many models with combinations of spectral bands. There's simple two-band ratios, or there are multiple bands used. So it really, there is no standard algorithm. So for demonstration purpose, again, we use these two, near infrared and red reflectance ratio for TSS, and references are given here. These are again derived from different lakes, not Lake Erie, but we are going to try and find coefficients for Lake Erie based on this band ratio. Similarly, for Secchi depth, these ratios are used from Sentinel-2 based on this paper here. So this is blue and this is red edge. Now, Secchi depth is, or water quality clarity, it's not that easy to obtain, but still empirical relationships are used here. Um, there are analytical models which are more complex. For our purpose and at considering the level of this training, we are going to stick to this band ratio models here. So there's some caveats and there's this caution regarding model selection and usage for water quality parameter retrieval. Uh, in this training, we have selected simple models based on band ratios as we saw for the water quality parameters. But a vast literature exists with a variety of models, linear and nonlinear, single band, band ratios, and multi-band combinations are all used. Each water body is different in characteristics, and it is recommended to explore, develop, and apply model algorithms for each sensor for the lake of your interest. So, not only each water body is different, and algorithm or models have to be derived for each water body, but each sensor is different too. So, if you develop a model for Landsat 8, those coefficients are not always going to work with Sentinel-2 or MODIS. So your models are sensor dependent as well as lake dependent. There are advanced and more complex models for water quality parameters that are based on neural network, artificial intelligence, and machine learning techniques are developed. Many researchers are working on these areas, and very complex and sophisticated models are available. But again, one has to train these models for the lake of your interest. Also, as many co-located points between in situ measurements and satellite observation should be used for developing the models. In demonstration today, we are just going to use limited samples from Gloria just to demonstrate how to do this. But in practice, you want as many points as you can find when you have satellite and in situ co-located measurements. And models should be validated by using independent in situ data. So you need a substantial amount of data to develop model, and you have some data to validate the model performance. So these are some of the things to keep in mind. So with that, we will start with a demonstration today. Sean McCartney will show how to derive statistical algorithm coefficients for acquiring water quality parameters. Again, considering the time we have, we'll focus on chlorophyll A and TSS, but we'll talk about Secchi depth or water clarity. The methodology will be similar, in which you use just different spectral bands to derive Secchi depth. And so with that, I'll hand it over to Sean. He will be starting his Google Earth Engine demo. And then you will also have time to explore the scripts and work with some of the data. Sure.
Well, thank you, Mita. In today's demonstration, I'll be showing how to derive statistical algorithm coefficients for acquiring water quality parameters, specifically chlorophyll A and total suspended solids, using Google Earth Engine. The first part of this demonstration will be showing how to take a spreadsheet, in this case a CSV file or comma separated values file, and bring this into a GIS so that we can create a shapefile and then bring that as an asset into Google Earth Engine to do some analysis. So in the spreadsheet, we can see we have a number of columns, everything from the site name to country, and we also have two very important columns, latitude and longitude. That is how we will define the locations to bring the spreadsheet into the GIS, specifically QGIS. And we also have a number of other columns such as chlorophyll A, total suspended solids, turbidity, Secchi depth, etc. So now that we've explored this file, what we're going to do is open QGIS, which is a open source GIS software that anybody can use on either a Mac operating system or a Windows operating system. And I'm going to go ahead and click New Empty Project. And then once I have that, to be able to bring the spreadsheet into the GIS, I'm going to go up to Layer, and you can see here the Data Source Manager. I'm going to go ahead and click on that. And what we have here on the left are a number of options for browsing for a file that we want to import. So I could import a vector or raster, but in this case, I'm going to be selecting the delimited text. I'm going to go ahead up to the file name, and I'm going to select the spreadsheet that I just showed to you with all the columns and rows. And after I select that file, we can see the file format. I want to make sure that the CSV or comma separated values file is the radio button that's selected. And then in the drop down under geometry definition, we want to confirm that the X field is the longitude field. These are all of the different columns that I can choose from the spreadsheet, but I want to make sure that X field is synonymous with the longitude and the Y field is the same as the latitude. I also want to confirm that the geometry CRS or coordinate reference system is selected to the EPSG 4326. And once I have all that, I'm going to go ahead and click Add, and then you can see that I'm going to go ahead and close out of this window now, and you can see that the locations have now been rendered in the map pane within the GIS. And to make a little bit more sense of this, I'm going to bring a base map into the map window. So I'm going to go ahead and go up to Map and then Quick Map Services. And then let's go ahead and bring in a Google Satellite view. And if I pan out just a little bit more, we can see that in fact, all of these locations are in the western part of Lake Erie. Lake Erie is a freshwater lake, a large watery body of water in between the countries of Canada and the United States. Now, if I zoom back in, what I want to do is open up the attribute table. So I'll go ahead and right click on the layer that I just brought in, that spreadsheet that I just brought in, and I'm going to go ahead and click on Open Attribute Table. And what I'm looking for are all of the dates around July 15th from 2019 that are co-located with the Sentinel-2 data that I'm about to bring in Earth Engine. So what I'm looking for here are every location where in situ data was collected in this lake from around the time of July 15th, 2019. Great. Once I have all of these selected, these are all of the in situ data points that were collected on this date. I'm going to go ahead and close the attribute window. And now if I zoom in to any of these clusters of locations, you can see that one of these points is highlighted in yellow, and I'm circling that with my cursor here. So each of those dates on July 15th, all of them that I selected are now highlighted in yellow. And what I want to do is export this specific date as its own shapefile. So to do that, I'm going to go ahead and right click again, and I'm going to go to Export, And then I'm going to go to Save Selected Features. These are the features that were from that specific date. And when I click on it, you can see that I have different options for format. I want an Esri shapefile, which is quite common, and I want to give it a file name. For now, I'm just going to give it a general name called test, and I want to confirm that the coordinate reference system, or CRS, is in fact EPSG 4326, and I also want to make sure that all of the different columns that came in with that CSV file are selected. And I'll scroll down just to make sure that everything else looks good. And once that's the case, I'm going to go ahead and actually, you know what? I'm going to select the location of this. So I'll go to the project folder in which I'm working. And I could save it there. I've already saved it, so this is just a demonstration for you. But this is how you would click OK, and then you would have a shapefile saved into a directory on your personal computer, be it a Mac or Windows operating system. So now that we have a shapefile saved from the location and date that we're interested in, and again, this date we selected because it was co-located with a Sentinel-2 overpass. To bring that in as an asset into Earth Engine, what I would like to do is go to Assets, and then we can go to New, and then I would say Table Upload, and then I would select the source files. And for that, I would navigate to the directory in which I saved the file. And you can see that the file is already saved in this directory. I would select the corresponding file types that are required, and you can see them all listed here, the allowed extensions. And so I would select all of those from this red button, and then I would select the directory that I want to save them in, and I would go ahead and click Upload. Now I've already gone ahead and done that, so you can see in my assets, I already have a asset that which I've named Lake Erie _ July 15th, 2019. Now if I want to bring this asset into my script, what I would do is go to the right arrow button, click on that, and you can see that, I don't know if you saw that, so I'll go ahead and delete it again, but you can see currently I have two imports, one named Gloria and one named Erie. So again, if I wanted to import an asset, I would go to the asset of my choice, and you can see the right arrow which says import into script, and when you click on that, there you go, that table now appears as one of my imports at the top of the script. Now I'm going to go ahead and delete this. If you wanted to, you can rename this anything you want. I'm going to call it test just for fun, but you can rename it anything you want. That's logical to remember. I'm going to go ahead and delete this because I've already imported the same asset, and I've already renamed it Gloria. And Gloria, if you remember, is the name of the data set, which is in situ freshwater in situ data that's been collected all over the planet. So that's why I gave it that name. And then also at the top of the script, we give some instructions such as what this training and the link to this training, if you ever wanted to come back, if you have access to the script and go back to the training page. And the start of the script is really selecting your area of interest. And to do that, you can go to the map window below, and you have different options for drawing a rectangle, and you can draw a bounding box around the lake or part of lake of your interest. You can also draw a polygon. That's another way of capturing your area of interest. And once you've done that, which I've already done, and then I renamed that bounding box, in this case I used a bounding box, to Erie to be congruous with the name of the lake. Now that's one way of defining your area of interest. Another way of defining your area of interest is what I just told you. If you have a shapefile, which you have for your specific area of interest anywhere on the planet, you can upload that as an asset and bring it in, import that into the script as well. So just different ways of constraining your analysis to an area of interest. The next section of code that we're going to be looking at is dealing with the Earth Engine Palettes module, which is a color palette module which was crowdsourced and created by the Google Earth Engine community. It's a really awesome community, and they've created this module for all public users to be able to use, to be able to visualize their different maps in the map window. So in this case, I'm going to define a variable, and then I'm going to pass the file path for the Earth Engine user community, which in this case is users, Gina, packages, palettes. And the next thing I'm going to do in this block of script is define a new variable, which I'm going to name palette. And in this case, I'm going to bring in the variable I just defined above, and then I'm going to specify the specific palette within that module that I'm interested in. In this case, it's the color brewer spectral, and this is defining the number of different palettes that I would like to use, which is part of this color brewer spectral. So in this case, I want to bring in all 11 options, and I'm going to reverse the order from the default that they give it to you. This next section of code is saying I want the base map in the map window to display anytime I run the code as the satellite option. Then this next section of code is setting the map center to a specific longitude and latitude, as well as setting the zoom extent. So anytime I run the code, it will pan to that zoom extent. And again, if I set this to 1, that would zoom out to the entire planet. And if I set this to 24, that would be the smallest region that Earth Engine allows you to render the map window. Then in this next section of code, I'm actually defining a variable to create a function. In this case, this function I am calling f, and then within this function, I want to return everything in the dataset of the Gloria dataset, and I want to return that and buffer all of the points within that by 10 meters. This 10 indicates the meters as the distance. So once I have that variable defined, and define this function, I want to go ahead and run a print statement or use a print statement as a gut check. And I'll show you what that means in 1 second. If I can just bring this out. So all of the print statements are going to go to this console tab, which is the middle tab within the 3 options on the right of the Earth Engine interface. And if I scroll to the top, you can see that I printed the buffered 10, and that is the feature collection that we can see here. And so if I'm interested in all the metadata, this is all of the different columns again that were from that original CSV file. They've all been brought in as the shapefile, and now I can see them all within Earth Engine once I use this print statement, as well as a lot of other metadata about each of the data points within each of the locations. So what I like to do, use a lot of print statements just as a gut check to make sure that I'm running the code line by line, that it's actually giving me an output that 1 makes sense, and 2 that is actually what is of value to me later on. So this next section of code is creating another function, and this is going to be a cloud mask function. So when I bring in the Sentinel-2 multispectral imagery bands, that I'm able to mask out all of the clouds and then return, and then also divide the updated mask by 10,000 so that I can bring the digital number for each of the pixels into a reflectance value. And that's why after we've masked everything, we divide by 10,000 so that we actually have a reflectance value from the original digital numbers. This next section of code is actually defining a variable for Sentinel-2, which Sentinel-2 MSI, that is the mission and the instrument which we'll be using for this analysis. And so once we've defined that variable name, I'm going to pass in the image collection, which is the Copernicus Sentinel-2 surface reflectance harmonized. And if you're ever curious about what any of these image collections are, I can copy and paste. And then when I go to the top of the window for searching the data sets, I can go ahead and paste that in. And then when I click on that, I can actually learn a lot more about what that image or image collection is. So it tells me about the description of the image as well as the bands. So I can see what each of the band 1, band 2, band 3, band 4, etc., all the way to band 12, as well as some of the terms of use. So anyway, so if you are interested in any of the image collections, you can always copy and paste that at the top of the script in the search bar and then learn more. This next section of this block of code is filtering the image collection to be co-located with the July 15th in situ data, the date that in situ data was collected. This next line of code is filtering that image collection by a cloudy pixel percentage, which is less than 20%. And then I'm going to map the mask to clouds function, which we defined up here. So I'm going to map that across all of the bands in this filtered image collection so that all of the bands which I am filtering are masked out for clouds. And then I'm going to filter the bounds by again, this is the area of interest, which I drew the bounding box around. So I'm going to filter it by the bounding box of Lake Erie, and then I'm going to use the median filter. So for any overlapping pixels within that date range, I'll take the median of all of the pixels that happen to be within this date range. And then again, I'm going to use a get check to use a print statement to print the results to the console window. So again, I'm going to use a statement here, filtered image collection by July 14th. And then we can see here again, filtered image collection July 14th. And sure enough, we have 23 bands within that date range that we filtered by. So this is just a get check to make sure that the code is performing as we want it to. This next block of code is setting visualization min and max values, defining a variable to set the min and max values. And again, these are reflectance values. Again, that's why we divided the image by 10,000 so that we could go from the digital number, how the bands originally come, to be a surface reflectance. And then we're going to select these bands for visualization purposes, bands 4, 3, and 2, band 4, 3 being the red band or red part of the spectrum, band 3 being green, and band 2 being blue. This next section of code is defining a variable for converting the buffered vector to a raster file, and we're going to be selecting the chlorophyll A from the buffered file that we defined above. Again, this is the buffered 10. So again, this is the variable that we defined to run the function to buffer all of the points that were in the CSV file. So we're going to define that variable, and then we're going to select just the chlorophyll A, and then we're going to return that. And what that's going to do is it's going to convert that vector-based file to a raster or an image file. And this next section of code is going to calculate the log 10 of the chlorophyll A image and then rename that to something logical, such as chlorophyll A or the log 10 of chlorophyll A. And then this next section of code, or I should say the next two sections of code, are using print statements just to make sure that the code, again, is performing as we want it to. And then this next section of code, lines 99 through 103, is defining a new variable, total suspended solids underscore buffer. And it's basically doing the same thing that we did just above here in these front lines of code. It's selecting the total suspended solids from the buffered locations that we brought in as a shapefile. And so we're just selecting just total suspended solids, and then we're going to create an image or a raster based file from that vector or feature class file. And then we're going to define another variable to rename the band from first to TSS, just so that we have a more logical name for that band. And then we're going to use another print statement just to make sure that the code is working correctly. And this next line of code from lines 111 to 126 is creating a histogram so that we can view the spread of all the values of chlorophyll A. And so that's what we're looking at here in this, again, this is on the console tab. And we can also, if you can see here, you can actually pop this out into another tab if you want to view it in much larger text and much larger font. And so this is just a way of exploring the range of values, the chlorophyll A values that we just subset from the shapefile. And this next sections of code are actually where we start getting into more of the algorithm development. So this next section is going to be calculating total suspended solids and the color index so that we can start doing some regressions. So this first section of code is calculating the total suspended solids, and we're going to do that by creating a band ratio. And in this case, it's going to be taking that filtered Sentinel-2 MSI band ratio. And in this case, we're going to be using the reflectance values for the near infrared, also the band 8 from Sentinel-2 MSI, and then the red reflectance, which is synonymous with the band 4. And this is the actual equation that we do to calculate the total suspended solids. We're going to take the log 10 ratio or the log 10 of the near infrared band and divide that by the log 10 of the red band. And then this next line of code is just indicating what the near infrared band is actually doing. It's actually synonymous with the band 8, and the red here in the text equation is synonymous with band 4. And then once we've derived that through that algorithm, we're going to rename the output total suspended solids _BR for band ratio. So this is a way of deriving total suspended solids from a log ratio of 2 bands from the Sentinel image collection, or Sentinel image, which is just the near infrared and red band. And then this next chunk of code is driving a different algorithm, in this case to derive the color index, which we will use to regress or perform a regression with the chlorophyll A. So in this case, we're going to, this is the algorithm here. We're taking the reflectance from the green and the blue and also the red, and we're going to perform this mathematical operations from, and then we're going to select these different bands, which again, the band 2 is synonymous with blue, band 3 is synonymous with the green wavelengths, and band 4 is synonymous with red wavelengths. And then once we've calculated that, we're going to rename the output CI, which again stands for the color index. And then we're going to use a couple print statements just again as a get check to make sure that the code is performing as we want to, so we can actually go down and see that yes, in fact, total suspended solids calculated and that renamed band is actually what we want it to be. And then again, from the color index calculated from Sentinel-2, that we have renamed it as we want it in terms of CI. So just making sure that the code is working properly. And this next lines of code from 161 to 165 is clipping that output to the bounding box around Lake Erie. Next, we're going to calculate the mean band values from the expressions above, and then we want to create the mean within the 10-meter buffered areas. And the result with this will be a feature collection. And so we're first going to define a variable, and then we're going to pass the expression that we created above for the color index, and we're going to reduce regions. And again, because we have multiple locations where all these different in situ points were collected, we're going to select reduce by regions, plural, and we're going to use the buffered 10, again, that 10-meter buffer around all these locations, and we're going to select chlorophyll A, and we're going to reduce by the mean. And we're going to set the scale as 10, and this again is in meters, and we want that 10 meter because this is the resolution, the spatial resolution of the Sentinel-2 imagery. And we're going to also specify the coordinate reference system, again to be EPSG 4326. This is the same coordinate reference system we've been using from the beginning. And once we have that feature collection with the color index, also with the chlorophyll A, we're going to use a print statement just to make sure that the output is working. And then we're going to do the same thing, but in this case, we're going to do it for the total suspended solids. And again, we're going to use another print statement just to make sure that the output is where we want it to be. Next, we're going to define a variable properties, and we're going to list the properties that are of interest to us for when we perform the regression. This is going to be chlorophyll A and mean. And mean is going to be the output when we ran the total suspended solid reducer and the color index reducer. You can see that we reduced it by the mean. And anytime you use a reducer, the default band name defaults to whatever the name of that reducer is. So in this case, because I reduced it by the mean, the default here, the output band, is going to be mean as well. So we want to define that variable of properties, and then we're going to define another variable, properties 1. So this is going to be for chlorophyll A, and then this next variable will be defined for total suspended solids. And again, use some print statements just to make sure it's working. And then we're going to create a new function to iterate over the list of properties, and again, these properties are what we defined right up here, and create an image from that feature collection. And then we'll have one image with multiple bands with the bands that we will need to perform the regression. And so in this case, I'm going to define a variable image, and then I'm going to pass the properties variable that we defined above, that chlorophyll A and mean, and I'm going to create a function. That function is going to be named property. And then within that function, I'm going to return the CI reducer, which is what we defined above. And we're going to select property, the name of the function. And then we're going to reduce the image, because again, we're going from a feature collection to an image. And again, we're going to use the function, the property function. And we're going to reduce by the first, and then we're going to rename by property. And again, that property being the names of the properties up here. So both chlorophyll A and mean. And after we use a print statement, just to ensure that the code is working as we would hope it to be, we're going to do something very similar, but in this case, it will be with the total suspended solids instead of with the chlorophyll A, because we want to derive the regressions for both total suspended solids and then separately for the chlorophyll A. And we'll use another print statement just to make sure everything is working correctly. Then we'll also create another histogram from in this case, it'll be from the chlorophyll log 10. And then just to make sure that we can see all the spread of values that we have within that histogram. And we'll use another print statement. And then next thing we're going to do is define another variable. And the whole purpose of this variable is just to rename that mean band to CI, or color index, just so that we have something more logical than just a very generic band name. And then we'll do the same thing for the total suspended solids band ratio. We're going to create a variable, total suspended solids band ratio, and we're going to pass in the image that we created above. Again, this is the image with two bands, both for the total suspended solid in situ data and then also from that band ratio. And then we're going to select mean, and this is that band ratio, and we're going to rename it total suspended solids underscore BR for band ratio. Again, we'll use a couple print statements just to make sure that the output is what we would hope it to be. So in this case, select a band by name, CI, and so we can just make sure that again, that band is being renamed appropriately. And then we're going to add bands we're going to define a new variable, image, and we're going to take the log 10 of chlorophyll A, and we're going to add the CI band to that. And we're going to do the same thing. We're going to add the total suspended solids band ratio. This is the ratio that we created from between near infrared and red. And then we're going to add that to the in situ total suspended solids. And then we're going to create some statistics. And this is just in case if any participants or future users or future colleagues wanted to export any of this as a CSV file. I just wanted to give the option of writing some lines of code to be able to generate a feature collection that one could export as a CSV file. And I'm also adding back in the latitude and longitude fields For, in this case, it would be for the chlorophyll A and color index, and for the stats 1, it would be for the total suspended solids. And again, lastly, I'll use a couple print statements just to make sure that everything is working correctly. And this last few sections of code are actually creating a regression. In this case, it will be a linear fit regression, which is the simplest regression available in Earth Engine. And we do this to be able to use to see a regression between the chlorophyll A and the color index. So we want to be able to derive both the slope and the y-intercept so that we can use this for the entire image of the color index instead of just for the specific locations that we have performed so far. So first thing we're going to do is define a variable linear fit, and then we're going to pass in the variable for the image that we derived above, and then we're going to reduce the region, and we're going to reduce it by the linear fit. And so this is again the type of regression which we're forming is linear fit, and we're going to define the geometry, which is constrained by the buffered 10. That's all of the in situ locations that were buffered by 10 meters. And again, this is the scale, 10 meters. And best effort true, use that just to avoid any error messages in terms of maximum pixels. And then we'll use some print statements to actually print the ordinary least squares regression output to the console tab. In this case, it'll be the offset and scale. So the offset being the y-intercept, and then the slope being the scale. So we've printed all this from that regression equation. And we're going to do the same thing for total suspended solids. So we're going to take the in situ total suspended solids measurements, and then we're going to perform a regression with the band ratio using the near infrared and red to find out the slope and the y-intercept for that. So we can see here, we also have the output. Once I use print statements, we've been able to derive the output for the y-intercept for total suspended solids and the slope for the total suspended solids as well. And so we can use this to be able to perform on any of the band ratios that we have to be able to derive that for the entire image from the entire Sentinel-2 image. And then this next section of code is adding all of the layers to the map window. So if I bring this up so we can see more of the real estate down here, we can see that I've output the color index, the total suspended solids, the imagery, which is, again, this is filtered by the median filter. And then these are all of the, if I zoom in, all of the in situ locations. This is the July 14th, 2019. And then if I zoom in a little bit more, we can actually see that these are some of the buffered areas that I derived a buffer around all of these different in situ locations. And lastly, we have the imagery itself, which is the Sentinel-2 imagery. So I've output all of these as layers into the map window. And lastly, this last section of code, if you choose to uncomment it, is to export the results in CSV format. So maybe you wanted to share this with a colleague who's not as familiar with JavaScript, and maybe they just wanted to work with CSV files. Well, we've created a couple lines of code to be able to use the stats variables and stats1 variables that we defined earlier to export. And to do this, you'll need to uncomment this code. So this is, again, up to you if you choose to do it. And then also, we've also provided the opportunity if you wanted to export any of the layers that we derived through this analysis as a GeoTIFF file and export these into your Google Drive to be able to bring into, say, a GIS to do more analysis. So this concludes the demonstration. I do hope that you enjoyed it. And again, this is the demonstration on deriving statistical algorithm coefficients for acquiring water quality parameters, both chlorophyll A and total suspended solids, using Google Earth Engine. I'll now turn it back over to my colleague, Dr. Amita Mehta. Amita, back over to you. Thank you.
Thank you so much, Sean, for the demonstration of theta weighing statistical algorithm coefficients for getting water quality parameters. And also, thank you for walking us through the script in GEE line by line. You will have chance to work with the scripts and replicate some of the results and try on your own to change things and see how coefficients change or your results change. Before you start working on that, let's summarize what we learned in this training. So in this training, we learned current and upcoming remote sensing observations useful for assessing water quality parameters in inland lakes. We want to say inland lakes because we mean freshwater lakes here, as opposed to coastal lakes or lagoons, which are brackish. So that's not what we are talking about. We selected in situ water quality parameter measurements to be used with satellite observations to maximize accuracy. Explored cyanobacteria assessment network, an early warning system to assess algal blooms in freshwater lakes. Used GEE to access Landsat 8, Sentinel-2, and Sentinel-3 optical reflectance data for water bodies of interest. Our case study was focused on Lake Erie, but you can replicate this for any other lake of your interest. We explored Gloria in situ water quality measurements and how to access those. Today we walk through algorithm development steps for water quality parameters based on remote sensing and in situ measurements. We primarily showed chlorophyll A and TSS retrieval. Very similar method can be used for water clarity using Secchi depth and different band combinations as we mentioned before. So this is what we did in this 3-part session. As I mentioned earlier, homework is posted today on our ARSET website and also on the training webpage. Answers must be submitted via Google Forms by August 8th. In the homework, you will find a Google Drive folder link where you will be uploading some of the screenshots that you've taken in part 1 and 2, and you will be doing the same today. So those of you who have attended all 3 live webinars and who complete homework assignment by the deadline would receive a certificate of completion via email approximately 2 months after today. We want to thank our guest speakers, Blake Schaefer, Jit Sagers, and Daniel Sobota. We also want to thank Dr. Nima Pelwan and Natasha Serov for their help with Gloria data and with base mission information. We are on Twitter. You can follow us, and we also have YouTube channel. Also, there are sister capacity building program developed in Surveyor that you can check out. So we will go to question and answer session soon, but before that, we're going to have some free time to work with the scripts that Sean demonstrated, and then we will start the question and answer session. So you have some free time to try the script and replicate some of the results. So we'll start with the question and answer session now. We have received several questions. Hope you were able to work with the scripts a little bit. And if you do have questions, please post them in the chat box. So we will start with the question 1. Is there any way to simulate a water treatment and determine how many times it will take for harmful algal bloom to come back in acceptable quantity? So yes, there are water treatment simulation softwares available. That is not our expertise, don't know much about it or haven't used those, but there are some links provided in the answer and that you can look at. So yes, that there are ways to gauge that how, what's the present water quality, and then what will you have to do to get how many times you will have to go through that to get a acceptable Heb count. So you can search around. There are softwares available. Question 2, is there any way to know the location of the lake where the cyanobacteria are concentrated? So in Cyan web app, we saw that it provides image of counts. And so that tells you where there are higher concentration of cyanobacteria. So you can, yes, from remote sensing data, you can see that. If you can resolve the lake, you can. How to download GeoTIFF images for selection location from the Cyan web page? I will have to go back and look into that and then provide this answer later on. Question 4, I want to know what are the bands considered by Cyan index, and also, if possible, the formula as well. We can relay this question to Drs. Blake Schaefer and Dr. Seegers, Bridget Seegers, but the reference is available here, describes how cyanobacteria index is derived, and both for Meris and Olchi, what bands are used and the formula used are shown there. Question 5 is, I would like to ask whether any processing has to be done to compare reflectance images from different dates. Yes, because when time changes, atmospheric conditions change. Maybe there are more aerosols or clouds, or so atmospheric correction has to be done when you want to compare surface reflectance. It also depends sometimes on solar zenith angle. So all those things have to be taken care of when you want to compare quantitatively. You can look at top of atmosphere reflectance images quickly and look at qualitative differences for sure. So it depends exactly what you're comparing. For surface reflectance, yes, you have to do the atmospheric correction properly. Question 6, I'm working on a project that uses drone imagery for water quality monitoring in South Africa. How can I share with you the in situ measurements of my study site? So there are two ways you can contact Gloria Data Coordinator here at NASA, Dr. Nima Palwan. His email address is provided here. Also, NASA Ocean Color Group has a forum, and you can join that and post this. If anybody is interested in situ data, you can communicate with them. Question 7, has there been any testing or parameterization of pace on lake or only over oceans? So there people have started looking at simulated pace data. So I'm trying to find out if they have been looking at lakes or not. Ideally, it is for coastal and open ocean because the pixel size is 1 kilometer square, but we'll get back to you on that one. Question 8, if it's impossible to collect in situ data for a lot of small lakes, is there a way to improve the generalizability of a model? Unfortunately, there's no definite yes or no, but unless you test clearly, there's no way of knowing. But what you can do is that you can use models developed for either nearby lakes or lakes which are similar in characteristics. Either they are Heb dominated or CDOM dominated or sediment dominated. Depending on that, you may be able to use coefficients derived for other lakes and then see the changes. You can definitely see changes by using those model coefficients. Quantitative accuracy, it cannot be judged without in situ data. Question 9, is there a rule of thumb for a minimum number of in situ measurements to develop algorithms for remote sensing images? As such, there is no rule of thumb, but you want statistically significant coefficients which they encompass all conditions. If you derive coefficients based on one season, and the next season, say chlorophyll concentration goes much higher in summer, you derive your coefficients in winter, it's not going to give you accurate results in summer. So depending on your goal, uh, you have better coverage in space and time, better coefficients, statistically significant numbers you will get. In literature, you see coefficients derived from tens of points, and then a couple of thousands of points. So there doesn't seem to be a rule, but I think you want to make sure that uh, those coefficients are statistically significant, and also that you are encompassing all the conditions that you are trying to cover. What we demonstrated today obviously is not ideal. We just use 8 points. That was mostly for showing, but more points you have, the better. More independent points you have, they have to have information. So that question 10, any suggestions for models of lake CDOM using Sentinel-2 MSI? This is one of the first papers that we've listed here. You may want to look at the paper for some information. Please explain a little more about the co-location concept. So ideally, when a satellite orbit passes over a lake and a sensor is looking onto the lake, right then if you collect water sample below where satellite is looking, that's ideal co-location in space and time. But that doesn't always happen for a number of reasons. First of all, maybe you cannot go out and take water samples, so you can plan it so that you can go within few hours of satellite overpass. Sometimes if you have in situ data and satellite is going over but it's cloudy, then you cannot connect surface. Satellite is not looking at the surface, so you don't have satellite data. So because of that, um, co-location can be within a few hours, within a few days. Ideally, spatial co-location within a few meters is good, a few pixels of satellite data. Question 12, is it possible to use model CHA concentration value derived from another sensor with co-located in situ data to derive an algorithm for another sensor without co-located in situ data? So again, you have to check whether it's going to work. If both the sensors you are looking at have similar spatial resolution, spectral bands are close enough, and bandwidths are close enough, then you might be able to use it, but you have to just check. Question 13, are these algorithms valid in high concentration of CHA such as CUMS? Is it necessary to apply a different algorithm in these circumstances? So there is again no standard algorithm that works in all cases. And if you go through this document where NASA algorithms are described, you will find information that there are several algorithms that are used for different sensors in different cases. Say for high chlorophyll value or low chlorophyll value, there are different models used. So you can get some idea if you read this document. But yes, I think any you cannot assume that one standard algorithm will work in all cases. At least you have to verify that it works, or to what extent it works. Would there be a bias correction needed? Would there be large errors? You have to sort of work through that. Okay, Sean, you want to address question 14?
Yes, I'm sorry. Yes. Question 14, is buffering a point vector data the same as interpolating to get a rasterized image? I could see how there might be uh, a lot of similarity and some confusion. So I would say it's not the same as interpolation. A fast and loose definition of interpolation is using multiple values instead of just one, but multiple values and multiple locations to create a continuous surface that can be used for mapping and analysis purposes. These are usually continuous quantitative data sets. But if you set your buffer at an unreasonable distance, say like if you're collecting data in situ and you set your buffer for something that's beyond reason, then there would be some level of interpolation and probably uncertainties that arise as you go farther away from that point location. In the demonstration, we buffered to 10 meters because we wanted to match the spatial resolution of the Sentinel-2 MSI image, and we didn't want to buffer too far from that known location of in situ data. So that's what we did there. And there are some similarities, but I would say that but they're not the same.
Okay, question 15. Can this method be applied with water quality in a pond? So that depends on two things. First of all, how usually ponds are shallow, so bottom reflectance would be an issue. So you want to test and maybe correct for it. And also depends on the size of the pond. Is it big enough to be resolved by a satellite sensor that you're using? So you can use these algorithms, but how accurate, that is something that you have to decide. It depends on the type of the pond. Question 16. Is there a way in GEE to correct data for sun glint? So I think that, Sean, you have question 16, you have put in an answer that there is a publicly available code using Earth Engine to correct for sun glint. And here is the code. Okay. Is there any part of the GEE code that would need to be changed in order to work for coastal saltwater ecosystems? If so, what are the specific changes that would need to be made? So first of all, you will have to have in situ data into coastal saltwater ecosystems that you can relate with satellite reflectances. So models can be similar, that empirical models, basically they just exploit information in different spectral bands, so that you can do, but you have to have in situ data where you actually want to retrieve water quality parameters. Question 18. What is the atmospheric correction used for harmonized Sentinel-2 being used in this demo? So harmonized Sentinel-2 data that we use, they are from Sen2 core. And so that's their standard atmospheric corrections being used, and you can look at this handbook for more information. Question 19. Are there rules of thumb necessary to apply for thresholds in CI, MCI, etc.? For when the concentration is high enough that the bloom is likely scum, or is it a separate algorithm like the floating algal index? We will have to get back to you on that one. I don't have specific answer on top of my head. Question 20. Is there a way to mask out the land pixels in the end image products for GEE? Sean, you want to address that?
Sorry, what question?
Question 20.
Okay, question 20. Yes, is there a way to mask out land pixels? There are some land and water masks that are available in GE. You can actually, if you go to the search terms, you can actually just filter by your search and you'll be able to find them. I would say the caveat being that in the spatial resolution we use today, the Sentinel-2 MSI harmonized product, that's a 10-meter spatial resolution. So if you're going to use the water masks that Earth Engine provides, those are derived from the MODIS instrument at a much more coarse spatial resolution at 250 meters. Some alternatives, if you're savvy enough, or if you want to challenge yourself, you can either create your own mask using different bands within Sentinel-2, or you can drive or source a mask, a water mask outside of Earth Engine, and then import that as an asset and then use that in your analysis. So those would be different options. Thanks.
Question 21, if multiple images are available with in situ matchups, is it better to develop the algorithm for only the image that's closest temporal match, or use them all and calculate the median value for a given pixel for all the available images within a certain time period around the in situ samples? So both these approaches have been used. If you look at the literature, that just temporal collocation is used, or there is median value used. And so I think you will have to just test it out, develop the algorithm, and then validate it with some independent in situ data to see which one gives you more accurate results. But if you look at the literature, both these approaches are used. If there are multiple images, then median value is used. Question 22, are there plans to launch additional Sentinel-2 satellites? So Sentinel-2C is also going to be there, will be launched next year. Question 23, when working with GEE, is it ideal to export the files into another application after producing a final classified image in order to apply color bars and final analysis? Sean, do you want to take that? Question 23?
Yes, 23. When working in EG, is that idea? Oh, got it. For pilot. Yeah, so this is, I think this question is for providing a very professionally looking map as your end product. So in the script that you have access to from the training page, we've posted that under part 3. We did provide a Earth Engine palette module. This was mentioned also when we were discussing the script. This is a crowdsourced palette, a module created by the Earth Engine user community. So there's a lot of different options for visualization, and you do have access to that through the script that we have provided for you. And I would also say that most analyses that people will attempt can be achieved in Earth Engine as well. So I would probably search around for what exactly level of analysis and what type that you're trying to do before trying to go to, say, QGIS or some Esri, ArcPro, etc. But I will say that if you want to get really creative with making a polished professional map, Earth Engine is not necessarily the best for that. So if you wanted to make something with a lot of detailed symbologies, changing different fonts and colors and moving text, annotating text, etc., you probably will want to export that final image into your Google Drive as a, say, a GeoTIFF, and then bring it into a GIS of your choice. Everybody has their own. I like QGIS because it's open source. Some people prefer to work in ArcPro or ArcGIS, and those certainly have plenty of tools to make the most polished final product. So I would recommend doing that if you had to present this to, say, somebody in your department and your job, or if you had to submit this for a publication. I probably would bring it into a different application to polish it up. Thank you.
Thank you, Sean. Question 24, how do you collect the Gloria Western area data like TSS, chlorophyll A, and Secchi depth? I'm not clear about the question. Are you asking about what methods were used, or it was collected by the Gloria team, and we shared the reference with you. The TSS and chlorophyll A were derived from lab analysis. Water samples were collected, and then lab analysis was done to come up with TSS and chlorophyll numbers. And Secchi depth was actually an observer would go out and dip Secchi disk in the water, and the depth where it disappears, you can't see it. That's the depth reported. So if you go to the the reference we provided for Gloria, the paper describes how these were collected. Also, there is a CSV file that provides which methods were used, if there were different methods used to derive these quantities. Question 25. I would guess that the average depth of a smaller lake is shallower than a larger lake. With the increasing resolution of satellite imagery, will there ever be a minimum size of resolvable lake based on its likely depth, if bathymetry is known, rather than its surface area and the spatial resolution of the satellite sensor? I think this is an excellent question, that it's not just the surface area, but it's the depth. It should matter. So because you want to be away from the edge for the lens effect, and also bottom reflectance can be avoided. So um, I am not familiar with the top of my head if that's how things have been done, but that's certainly a great suggestion and we can look into that. In question 26, how have you incorporated the field measurements in this GEE code? If not, could you please share GEE code that incorporates the field samples and then calculate water quality based on those samples, which also provide the RMS or correlation between field measurements and measurements made by satellite data? So Sean, you may want to address that, but yes, Sean provided shapefile for Gloria in situ data. Sean, you want to address question 26?
Yes, question 26, incorporated field. Yes, so the field measurements have been brought in. They were brought in as an asset. That asset has been shared with you. It's part of that script. So if you go to the imports at the very top of that script, you'll see that you'll see that table, which was imported as a shapefile, is there. Now, if you wanted to work with any of the other data sets that weren't co-located for that specific date, that date being in the script July 15th, 2019, we did provide a CSV file, which can also be found on the training page, which has all of different options for co-locating Gloria data with Sentinel-2 data. So you can do that. And another option would be to go to the, if you don't find the lake and the date within that CSV file that we've provided on the training page, you can go to the Gloria website and you can try to find dates that where you can co-locate with Landsat, one of the Landsat missions, or Sentinel-2, et cetera, maybe a mission of your choice. So those are different options, but the code is there if you wanted to do that. So yeah, thanks.
So question 27, if we have a list of sampling points from different lakes and the sampling is done in different years, how to automate this process? Is there a function written in JavaScript that does this, as far as you know? And I think Sean has provided a link here.
Yes, I provided a link to a publication that does just that. They used Earth Engine to and some algorithms to be able to co-locate different satellite surface reflectance with in situ data on multiple dates over multiple lakes. So I would refer that our participant who asked that question to the link that we've provided. Thanks.
Question 28 is, will it be necessary to use codes for cloud masking if we use cloud-free image instead of image with cloud coverage? So if you use level 2 data, like we have done here, cloud information at each pixel is available. So based on that, you can mask it. So or you can at least make sure that it is cloud free. If you are confident that there are no clouds in this scene and you want to use the data as is, then perhaps you can. Question 29, my Google Earth engine is not exporting anything to my Google Drive even after uncommenting the lines and making sure my accounts were the same for the GEE and Drive. What might be the cause for this and how can I resolve it?
Yeah, I would say I would answer this, it depends on how large the file is. If you're working with, say, Sentinel-2 data, these are very large files, and especially if your domain, the area in which that you're trying to export from, if it's quite large and that file is large, this will take some time. So I would, one, check the status of the export just to make sure that it is indeed attempting to export. If you're not even getting to that point, that could be something else, in which case, definitely reach out to me. I've provided, my name is Sean McCartney. I provided my contact information on the PowerPoint, so you can certainly reach out to me. Please, when you do, explain the issue and also send a link to your code. That will help me to troubleshoot your issue. But I think a lot of times the most common is if you're working with a large file, it just takes a long time for the export to go through to your Google Drive. So I would give it time, definitely at least 20 to 30 minutes, and it could be even longer depending on the size of the file, and definitely refresh often just to make sure that maybe sometimes if you're not refreshing, you might not see it within your drive. So those were the first two things I would do. And then if you're still having issues, say like tomorrow, if you're still not able to export it, please do send me an email with a link to your code. Thank you.
You may want to look at question 30 and 31 as well, Sean, if you don't mind.
Great, yeah, so it's how can you get longitude and latitude within the GE code without getting from somewhere else? So there's different ways to do this. In the Gloria files, which we imported as assets, there are columns which have the latitude and longitude. So if you're working with Situ data and you're bringing it in from, as a shapefile or somewhere else, there you should have ideally at least those columns that specify the locations for latitude and longitude. And those have been provided in all of the Gloria CSV files that we've been using in this training from part 1 till now. So, and then another way, if you're just curious, if you just want to know, say, a latitude and longitude in general within GEE, if you're in the map pane, so below the code editing section on the top, if you go to the inspector tab, which is on the upper right portion of Earth Engine, and if you click on that tab, and then if you click anywhere in the map pane, the first line that you'll see as a result will be the longitude and latitude. So that's a quick way of investigating a specific location without having to, use any code to query a file, et cetera. That's just a quick way of inspecting where that location might be in terms of latitude and longitude. Thanks.
So next question is about QGIS. How can I get the Google satellite option? I know that there is a plugin, a quick map service. I think that has all the map options. So you may need to install that plugin. Question 32. When you filter the image collection for a specific date, the optical images may have a high percentage of clouds, but our AOI might be cloud free. So when you apply a filter, it considers the total percentage for clouds in the whole image, leaving out some of them that might be useful for AOI. How can you apply filter cloudy granular considering not the entire optical image, but just the area of can you check that precisely without checking each date? So it is not just AOI. When you cloud mask, like we have done for Landsat 8 and Sentinel-2, it is each pixel is checked. Yes, of course, if you go to Earth Explorer, you can also see that entire image, what part is cloud free and what's not, that's available. But in here, each pixel is masked as cloudy or not cloudy. So you're not really, when you look at your AOI, you are looking at each pixel within that and saying whether this is cloudy or not cloudy. Question 33, what about the solution using a geospatial model? We are only concentrating on monitoring. What about an algorithm which can lead us to solve the problem within a remote sensing method? I'm not sure I clearly understand what that means. We're only concentrating on monitoring. What about an algorithm which can lead us to solve the problem within a remote sensing method? I'm sorry, but I'm not clear what the question is. Question 34, are there other sensors used to detect monitor algal bloom other than optical, multispectral, hyperspectral? So open source satellite data that we have mentioned here, they are used for monitoring algal bloom. There may be commercial optical data available, but these are open source. There are satellites, um, international satellites are there, which we are not talking, we have not included. These are European satellites are included, but there is also a Korean satellite, I think Kochi. So there are other international satellites that may be providing the same information. Question 35, is it possible to derive lake bathymetry using satellite derived data? So there is a mission ARSET-2 that provides information about lake bathymetry based on LiDAR observation. So two important notes here. We will post this question and answer on our website in a week or so, so that you can go back and look at those. There will also be a survey sent to you, this end of training survey that ARSET sends everyone to get your feedback. So if you take time to complete the survey, it helps us. It's coming, it will be sent to you via email. So we're almost out of time here, and we really want to thank you for attending this entire webinar series. And hopefully we'll see you in our next training as well. You have our contact information, so please do not hesitate to contact. So again, on behalf of the entire ARSET team, we want to thank you. Also want to thank the team here, especially my colleague Sean McCartney, Selvin Hudson-Odoi, Natasha Johnson-Griffin, Sarah Cashel, Jonathan O'Brien, Brock Blevins, and Sue Monty. All of them have helped in coordinating this webinar series and helped in many ways. So thank you all, ARSET team, and again, thank you all for attending this training.